Imagine trying to balance a 700-ton block of hollow concrete in midair. You're inching it forward over an empty void, all while driving it across a bridge that is actively building itself right beneath your tires.
Yes, an incredible mental image, right?
Right. And the main reason you are doing this incredibly precarious balancing act, to avoid stepping on a single irrigation ditch, like 10 meters below you.
It completely upends the traditional view of heavy infrastructure. Usually,
Yeah.
you clear the ground, pour a massive foundation, and just build up.
Yeah, the normal way.
Exactly.
Yeah.
But here, the ground was totally untouchable. The engineers had to treat the airspace above the landscape as their construction site, operating entirely suspended.
Which is exactly the vantage point we were taking for this deep dive. Today, you are piloting a virtual drone over the flat, deeply green alluvial plains of southern Taiwan.
It's a gorgeous area.
It really is. We are running a highly targeted flight path over the Taiwan high-speed rail, specifically a 2.5-kilometer stretch from Chainage, 249.5K to 252K. Our mission is to analyze this exact flight path purely through a civil engineering lens.
Which means looking at some truly massive viaducts.
Exactly. We'll look at those viaducts, the environmental challenges, and the architectural marvel of the Chiayi HSR station.
Okay, let's unpack this. Pushing the throttle forward, our drone is officially in the air.
So to ground what you are looking down at, you have to consider the scale of the THSR system. I mean, the entire line is 345 kilometers long.
That's a massive footprint.
It is, but what really stands out is that 76.4% of that route, so over 252 kilometers, is built on elevated viaducts.
Wow, most of it is just in the sky.
Basically, yeah. As our drone lifts off near the 249.5-kilometer mark, you're looking down at a section of the Chiayi Viaduct. And get this, until 2010, this specific continuous structure held the record for the world's longest bridge. The longest bridge in the world.
Yeah, stretching 157.3 kilometers.
So we have this endless gray ribbon slicing through an ocean of cultivated farmland. The obvious question isn't just why they elevated it, but how they managed the footprint.
Right, because you can't just pave over that kind of land.
Exactly. The sources point out this area is intersected by shallow, flood-prone rivers like the Pachang and the Chishui. If you build a traditional ground-level embankment, you essentially build a 150-kilometer dam across a natural floodplain.
Which would be totally catastrophic for the local agricultural ecosystem.
Yeah, I'd imagine the farmers wouldn't be too happy about a massive dam.
Not at all. The land here relies on a highly complex, really delicate network of irrigation canals. Elevating the track allows the hydrological cycle and the farmers to operate completely uninterrupted while trains pass overhead at 300 kilometers per hour.
That's incredible.
It is, but the environmental preservation mandate created an enormous logistical hurdle. I mean, you cannot drive convoys of heavy machinery through vital rice paddies to pour concrete pillars and decks on site.
Which brings us to the full-span precast launching method, or FSPLM. It sounds like a giant Lego set snapping together. But how do you build a 157-kilometer table over active farmland without disrupting the entire agricultural ecosystem below?
Well, you have to pre-build the pieces. We know the standard box girders used here are 13 meters wide, 30 meters long, and weigh 700 tons apiece.
700 tons, just for one piece.
Just one. So precasting them in off-site factories keeps the mud out of the fields. But the delivery mechanism is what's really brilliant.
Right. How do you even move something that heavy?
They load this monolith onto a specialized multi-wheel trailer and drive it right over the top of the previously completed bridge sections.
Wait, so it uses the finished structure as its own exclusive delivery highway?
Exactly. When the trailer reaches the end of the line, a massive piece of equipment called a launching gantry takes over.
Like a huge crane.
Sort of. The gantry essentially acts as a temporary truss, bridging the empty gap between the finished deck and the next empty pier. It receives the box girder, slides it forward along its own rails over the void, and precisely lowers it onto the bearings of the new pier.
Okay, wait. If the bridge builds itself forward using its own completed sections, doesn't that put an immense, compounding stress load on the newest, greenest concrete that just set? You're driving thousands of tons of machinery over a span that might be only days old.
Yeah, that is a critical constraint, and it dictates the entire material science of the girders. They aren't just solid blocks of poured concrete. They rely heavily on post-tensioning.
Post-tensioning, meaning what exactly?
So inside the concrete walls of the box girder are ducts containing high-strength steel cables. Once the concrete reaches a specific initial strength back in the casting yard, hydraulic jacks pull these cables incredibly tight and anchor them.
Oh, I see. So it's squeezing the concrete together.
Precisely. Actively compresses the concrete. Concrete is naturally weak in tension, but incredibly strong in compression. By pre-compressing it, the girder achieves immense structural rigidity almost immediately.
Which lets it handle the weight of the next delivery truck.
Right. It can handle those massive dynamic loads long before it would have naturally fully cured.
So the structure is exceptionally rigid by design, but, as our drone cruises forward past the 250-kilometer mark, we run into a major contradiction. A continuous, highly rigid concrete table is the absolute last thing you want when the ground beneath you is a highly active seismic zone.
Oh, absolutely.
Taiwan is basically an earthquake factory. How do you keep a continuous concrete ribbon from just snapping in half when the alluvial plain underneath it starts violently shifting?
Well, you have to introduce controlled flexibility. This section, which was recorded in the project files as Lot C280 and built by a joint venture including Samsung, Doosan, and IE&C.
A lot of big international players.
It's very big. This section features seismic design based on a 950-year return period earthquake.
950 years?
Yeah, that represents an incredibly rare, catastrophic seismic event. The engineering mandate here isn't to build a structure so rigid that it takes zero damage. If you try to fight a massive earthquake with pure rigidity, the concrete will simply shatter.
It's more like a spine, right? It needs to be rigid enough to hold the body up, but articulated enough to flex when the environment throws a punch.
That is a perfect functional comparison, actually. The design utilizes a philosophy of ductility. The connections between the box girders and the piers incorporate specialized elastomeric bearings and seismic dampeners.
Like giant shock absorbers.
Exactly like that. These devices isolate the deck from the ground movement, absorbing and dissipating the lateral shear forces. Furthermore, the piers themselves are designed to form what civil engineers call plastic hinges during a massive quake.
Meaning you intentionally design specific sections of the concrete column to yield and bend without fully breaking.
Yes. The steel rebar inside the pier is configured to deform plastically, which absorbs massive amounts of kinetic energy. The column might sustain heavy, visible damage and need substantial repair, but it maintains its vertical load-bearing capacity.
So the deck doesn't collapse.
Exactly. That fulfills the ultimate safety mandate. The structure maintains its integrity long enough for the trains to safely come to a complete stop.
Which introduces the technology side of that survival equation, right? A highly articulated bridge keeping the deck in the air is only half the battle. If a train plows into a warped section of track at 300 kilometers per hour, the kinetic energy of the derailment alone would be devastating.
Right, which is where the Disaster Warning System, or DWS, actively communicates with the physical infrastructure.
How does that work?
The entire route is lined with a localized network of sensors monitoring wind speed, heavy rain, flood levels of those shallow rivers we mentioned, and most importantly, seismic activity.
So it's constantly listening to the environment.
Yes, and the DWS is calibrated to detect the initial, faster-moving P waves of an earthquake. Those are the compression waves that arrive just before the destructive shaking S waves.
So it detects the warning knock before the door gets kicked in.
Precisely. The moment those P waves register, the DWS instantly triggers the automatic train control system. It automatically cuts the power supply to the trains and initiates emergency braking protocols across the affected sector.
All before the real shaking even starts.
Exactly. The goal is to shed as much kinetic energy as possible before the S-waves arrive and begin heavily manipulating those plastic hinges and bearings we just discussed.
Building this is one thing, but trusting it is another. It feels a bit like building a house of cards on a wobbly table. How do we know the math actually holds up in the real world? A dropped decimal point on the bearing capacity calculation compromises the entire survival model.
It does. It forces the question of trust.
Right. How do you guarantee that a massive consortium of international builders isn't quietly optimizing their profit margins by shaving tolerances?
You eliminate self-policing through a system of extreme, multi-layered oversight. The THSR project utilized an aggressive auditing framework involving ICE and IC systems.
ICE and ICE?
Yeah, IC stands for Independent Checking Engineers, and IC is Independent Site Engineers.
I want to break down how that actually functions in practice, though. It can't just be a second set of eyes glancing over the blueprints and stamping an approval.
No, it is much, much more rigorous than that. The joint venture contractors had their own checking engineers to review initial designs, but the THSR Corporation required completely independent third-party ICE firms to perform parallel verification.
Parallel verification.
Meaning the ICE firm takes the raw geological and architectural requirements and calculates the load-bearing requirements, the shear stress tolerances, all of it, completely from scratch.
Oh, wow. So they run blind parallel calculations to see if their mathematical models match the contractor's models. So if the primary contractor says they need 40 tons of rebar in a pier to survive the earthquake, the ICE firm has to arrive at that exact same number independently. And if they don't, work stops.
Work completely stops until the discrepancy is resolved. And that's just the theoretical side. The ISE firms, the independent site engineers, are physically on the ground validating the execution.
Watching them actually pour the concrete.
Right. They are testing the slump of the concrete pours, verifying the post-tensioning force applied to the cables, and ensuring the physical reality matches the mathematically verified blueprints.
That is incredibly thorough.
And there's more. An IVNV, an independent validation and verification engineer, audits the entire holistic process. There's literally no structural opportunity to cut a corner because every decision is challenged by a parallel independent entity.
This level of precision is crucial because as our drone approaches the 251-kilometer mark, the geometric simplicity of the track just vanishes.
Yeah, the landscape changes entirely here.
Looking through the camera, we can see the standard two-track viaduct we've been following suddenly expands massively outward. The contract required the engineers to transition this structure to accommodate a sprawling four-track layout as it approaches Chiayi Station.
Right, and it also had to integrate a sideline branching off to the Taibao maintenance base.
Which sounds like a nightmare. It's like a highway suddenly adding express lanes while suspended 10 meters in the air. Here's where it gets really interesting. How do they manage that sudden weight and width transition?
Well, this specific junction completely invalidates the construction method we discussed earlier. The FSPLM, with its precast girders and launching gantry, is incredibly efficient for straight lines and uniform curves. But it is fundamentally incapable of handling variable geometry.
Because you can't use standard puzzle pieces when the shape of the puzzle is actively changing. You have to pivot your entire construction methodology in midair.
Exactly. The engineers had to shift away from precast blocks and employ highly customized in-situ construction methods. The sources highlight the use of movable scaffolding systems, or MSS, and the balanced cantilever method, or BCM.
Let's dig into the mechanics of the balanced cantilever method. To an informed observer, building a massive concrete structure over active transit corridors without ground support seems counterintuitive. How does BCM solve the problem of these widening tracks?
BCM essentially operates on the physics of a seesaw. Instead of spanning a gap between two piers simultaneously, you start at a single central pier.
Okay.
You place a piece of equipment called a form traveler on top of that pier. You then pour a segment of concrete extending outward to the left and immediately pour a corresponding segment extending outward to the right.
Oh, I see. So you are building the bridge deck in both directions at the exact same time, using the weight of one side to perfectly counterbalance the weight of the other.
Yes. As the concrete cures, you tension steel cables through the new segments to lock them to the central pier, move the form travelers out to the new edges, and just repeat the process.
That's genius.
It really is. This allows you to build incredibly complex curving or widening deck shapes out over the void without needing a single piece of scaffolding touching the ground below.
And for the areas where BCM isn't optimal, they utilize movable scaffolding systems. I imagine this functions somewhat like a massive underslung cradle.
That is essentially it. An MSS is a gigantic steel framework that clamps onto the existing bridge piers. It provides a massive temporary floor high up in the air.
So workers can literally just walk around up there.
Right. Workers lay out custom rebar configurations for highly irregular deck shapes and pour the concrete directly into place. And once it cures, the entire steel scaffolding system hydraulically unclamps, walks itself forward to the next set of piers, and clamps back on.
That combination of MSS and BCM is what allows the viaduct to swell from 2 tracks to 4 tracks to support the Chiayi Station bypass lanes. But widening the physical deck introduces a severe dynamic load problem.
It definitely does.
You now have a platform where a stationary local train might be boarding passengers on the outer tracks, while an express train blasts down the center tracks at 300 kilometers per hour. How do they prevent the vibration of the express train from jolting the waiting passengers or tearing the widened pier caps apart?
It comes down to mass and stiffness. The widened pier caps are heavily reinforced continuous box structures. They are specifically designed to absorb and dampen those specific vibrational frequencies.
So they just absorb the shock.
Exactly. The sheer mass of the cast-in-place concrete deck, combined with specialized ballast mats under the track beds, prevents the kinetic energy of the express train from propagating laterally across the platform.
The result of that vibration dampening is what drives the operational success of the THSR. The system maintains a 99.8% punctuality rate, with an average delay of only about 4.2 seconds.
Which is almost unheard of for a system this complex.
It's crazy. That metric is only possible because the infrastructure allows for this seamless kinetic flow. Local trains can decelerate and pull onto those rigid outer platforms, clearing the center lines, allowing the express trains to maintain absolute maximum velocity through the station zone.
It is the physical manifestation of operational efficiency. And, as we follow those 4 tracks into the station zone, the engineering focus shifts from purely kinetic survival to human interaction.
Bringing our drone to a hover directly over Chainage 251.4K, we are looking top-down at the architectural centerpiece of this flight, Chiayi Station.
It's a stunning piece of architecture.
Designed by Fei and Cheng Associates and built by the Takanaka Corporation, it sits directly atop that heavily reinforced, widened viaduct. The sheer volume is impressive, over 21,000 cubic meters, comprising a massive framework of steel and reinforced concrete.
Right, and from a structural perspective, the station utilizes a space frame design. The station hall roof and the platform roofs are horizontally connected, creating a unified, continuous canopy over the tracks.
Which looks great, but I imagine it's highly functional too.
Oh, absolutely. Connecting the roof structures enhances the overall stiffness of the station against high wind loads from typhoons. It basically acts as a massive aerodynamic shield for the platforms below.
But looking through the drone's camera at the dead center of that unified roof canopy, there is a massive, perfectly oval-shaped skylight. It's like a giant eye staring back up at our drone.
Yeah, it's a very prominent feature.
But wait, we've talked so much about rigid, survival-focused engineering. How does a massive glass hole in the roof fit into the safety-first mandate? Doesn't carving a massive geometric void into the center of your roof fundamentally compromise the sheer resistance of the canopy during a massive earthquake?
What's fascinating here is how the architectural design functionally compensates for the void. The perimeter of that oval skylight is heavily reinforced with a massive steel compression ring.
A compression ring?
Yeah, it takes the lateral forces that would normally travel straight through the roof diaphragm and smoothly redistributes them around the opening, much like water flowing around a boulder in a stream. The void doesn't weaken the structure. The load paths are simply rerouted.
Oh, wow. Which means the engineers could fulfill the strict low-carbon mandate of the THSR without sacrificing safety. That skylight acts as a massive solar funnel, flooding the central concourse with natural daylight.
Exactly, which significantly reduces the electrical load required for artificial lighting. And the environmental integration goes even further. The design incorporates extensive eco-friendly solar panels across the remaining roof surface. These panels transform a static transit hub into an active generator of renewable energy that feeds back into the local grid.
And the integration extends to the ground level, too. Peering down past the station concourse to the street, the kinetic flow we saw with the express trains is mirrored in the urban planning. The station anchors a continuous loop of transit vehicles right out front.
Right. You are looking at the Chiayi Bus Rapid Transit, or BRT, system. The integration between the THSR and local transit was so highly prioritized that the BRT was temporarily launched on the exact same day this high-speed rail segment opened in January 2007.
Just to make sure they were perfectly synced up.
Exactly. The station is engineered as a seamless kinetic funnel. It takes a passenger traveling at 300 kilometers per hour, decelerates them onto a stable platform, flows them down through a naturally lit concourse, and deposits them directly onto a rapid transit bus connected to the broader city grid.
It is a phenomenal orchestration of scale. Well, our virtual drone has reached the end of its battery life, and it's time to bring it in for a landing. We have only covered 2.5 kilometers of track today, flying from 249.5K to 252K.
A very short distance, all things considered.
Right, yet in that incredibly brief window, we've decoded a dense layering of structural mechanics.
We observed the FSPLM delivering 700-ton post-tension girders over an active agricultural grid, effectively building a bridge from the sky down.
We analyzed the ductile engineering of plastic hinges and elastomeric bearings designed to yield without collapsing against a 950-year earthquake, all backed by the rigorous parallel calculations of IC and ICE auditors.
And we looked at the seesaw physics of the balanced cantilever method and the hydraulic steel cradles of the movable scaffolding systems, allowing the track to widen midair to support station bypass lanes.
And finally, we hovered over Chiayi Station, where compression rings and space frames allow a massive skylight to coexist with typhoon-grade structural integrity.
It's a lot to take in. But if we connect this tightly focused drone flight to the bigger picture, the civil engineering execution over these 2.5 kilometers represents a masterclass in environmental mitigation and geological survival.
The ultimate takeaway for you listening, the next time you are sitting comfortably on a train moving at 300 kilometers per hour, or even just looking up at the concrete underside of a local highway overpass, keep this flight in mind.
Yeah, you are suspended by an invisible, highly calculated ballet of sheer mass, independent auditing, and controlled flexibility. And it leaves me with this thought. If engineers can utilize these methods to construct massive grids across active fault lines without disrupting fragile hydrological networks below,
Right.
what does this mean for the future of our most vulnerable coastal cities? As climate change alters sea levels and floodplains, could the elevation techniques, the parallel auditing systems, and the ductile seismic designs used right here in Chiayi become the foundational blueprint for raising entire urban transit networks above the rising tides?
Something to really think about. Keep questioning how the world is built around you.